Chris Kurzik from AES. Welcome back. A little bit about our company, what we do. We provide equipment re-rating and fitness for service services, and reliability and safety studies, short-term staffing that we've been providing, and training and certification, materials and welding studies and investigations, and estimating and economic evaluations. And we've been getting into environmental studies like carbon footprint and emission studies. So let's dive into what we're going to work on today. We're going to continue our studies of fatigue, and we're going to go through the weld and metal fatigue basics before we proceed into ASME to build up a good strong understanding. And so we're going to go through defining fatigue. We went through the causes of fatigue and the stages of fatigue in the last few videos in stage 1. And in this stage video, we're going to continue onwards, looking at propagation, stage 2 and 3. And then further on, we're going to be looking at, in the future videos, factors affecting weld fatigue, fatigue nucleation, and the topics shown here. So let's continue with propagation, non-propagation, stage 2 and stage 3 cracking. So propagation and non-propagating cracks. So this is really important, and we spend a little bit of time because a lot of the problems when you look at cracking is okay, so you have a crack present, but if we say derate the pressure of a vessel, or do something to reduce its capacity, maybe lower the tank level so the stresses are lower. Perhaps as a strategy, these cracks will stop propagating, and we'll be able to run this equipment indefinitely. I mean, that's a valid strategy, right? And so there's we have cracks that still remain sharp, and then we've got non-propagating cracks where there's some ductility in the tip, and it serves to blunt the material. So the propagating and non-propagating then really depends on the amplitude of the fluctuating load or the stress ratio and the toughness of the material. If there's a very tough material, then you have a very good chance of blunting those cracks. So we're going to talk a little bit more about crack and propagating and non-propagating crack. I've got a few figures here we'll talk about. So cracks propagate due to the sharpness of the crack tip. Okay, that's the first thing. And if the material is plastic, it can deform the tip and then blunt the crack growth. So if you have a very tough material with a lot of ductility and it can strain harden a lot, then it can really serve to blunt the crack tip and prevent the growth. So the first diagram is a simplified sharp crack tip. You can see the tip of the material here, which is shown here, and you can see how the crack can start to keep going under those type of situations, right? Now we have another situation where the forces may not be as high and this material is quite hard, and then over here in this part here is like the blunting, because this area, the red part here, is like a plastic region, and it serves to blunt the crack growth. Look at a curve. It's called the stress SN curve, or the Wooler curve, and it's a very interesting way to look at materials and how they behave in fatigue. And there's a whole tons of data out there for different alloys and materials, looking at their fatigue properties. What's very interesting about that is this fatigue limit that you see right here. And looking at the fact that ferritic steels, they have a fatigue limit and where the cracks don't propagate. And so if your stresses are below the fatigue limit, then your part can continue on forever. But other materials such as aluminum, they'll definitely have a life, and they're not as blunting as steels are. And that's the beauty of steel, is that it can handle a lot of cracking and abuse, and it can continue on for a long time. So that's the SN and the Euler curve. And so let's continue. So we're going to go look at the second part of this. Is called the stable crack growth, stage 2. So factors that affect stage 2 cracks. Crack propagation is determined by the maximum stress range, the maximum stress minus the minimum stress. That's the definition. That's a term that's used, by fracture mechanics people. So it's basically trying to understand, the amplitude, right? And then the crack propagation is also determined by the microstructural characteristics. So if you look under the, you might look at the grain size, that's size, and the shape of the grains, and the distribution of the second phase particles in the matrix. So if you have a lot of very hard particles like microstructural particles like martensite, then they're very, very brittle, and they can contribute to crack growth. So those are the factors that are associated with this. Now, we continue this, so let's continue with more discussion on that. So, as a rule of thumb, if we increase our yield strength, we will reduce our ductility. Okay, this is not every case, but typically for carbon steel, mild alloy steels, and if we decrease our yield strength, we drop our ductility, but we increase the crack growth rate. And this is due to the reduction in extent of plastic deformation experienced by materials ahead of the crack tip under the influence of an external load. And if you want to increase the blunting of a crack tip, you decrease the growth rate, and you decrease the stress concentration. So that's how important the blunting effects are. So we're going to continue on to stage 3, and we'll talk more about that. So you can see over here in this part of the graph, we had a sudden appearance of a crack due to the nucleation, and that's sort of the threshold stress. And then we moved on to this constant growth rate, kind of modeled with Paris's law. And then suddenly we've got this fracture that occurs, and we're going to talk more about this sudden failure. This is the most undesirable part, because that's when the part ends its life, right? And so we'll continue with this. So we got this unstable fracture. It's characterized by a catastrophic failure. So it's unstable crack growth, which causes abrupt fracture. So basically, it's an overloading event that occurs when the applied stress, right, exceeds the tensile stress due to a reduction in area, because that crack across the cross section of that part will decrease the cross-sectional area, and of course the tensile stress is the force divided by the area of the part. So if the area, cross-sectional area, is reduced because the crack grows, and then there's less area left to carry the stress. So then as the crack grows, the stress grows. And so that's basically the mechanism for what happens. So it's a motor fracture, and maybe ductile or brittle. It depends on the type of material and how it fails, because sometimes the part at the end can neck a little bit and then fail if it's it's high ductility, or if it's like cast iron, it'll just suddenly snap and break. And so it exhibits those properties. And of course, that's all temperature dependent, because if you have, a very, very low temperature material and it hasn't been it's not rated for those temperatures, then even a ductile material can act like a brittle material, right? And if you want to know more about it, it's called MDMT, and it's found in our earlier videos. We made a whole bunch of videos on that, so we can understand, how those engineering issues are handled. So look at the growth rate and residual fatigue life. So this is an interesting curve because it shows on one side the crack length, and so A0 over here is the initiation of the crack, and then we continue. Our crack length goes to a critical crack length called AC, and then we go to the final, the rate and through the number of cycles of the part, and we have characteristically the crack nucleation is actually probably a little bit shorter than that. And then we've got the stable range, where it's flat and fairly predictable. And then we've got our last stage where the crack really starts to rise. And of course we have our point of fracture, which is called NF. So it's a slightly different way to look at it. I really don't use this chart. I prefer to use the one previous, because it seems to contain a lot more information, but that's all preference, of course. I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.